Okay, so you had a question about this. What is the question? Okay, so you see the wave function psi, is a function of x. And so we're saying if we evaluate that wave function at minus x, so this side, does it equal that side times plus or minus 1? And if it's times a plus 1, like look at the green curve. So the psi at negative x is equal to plus 1 times psi of positive x, because they have the same value and the same sign. But the red curve, psi of negative x, is equal to minus 1 times psi of positive x. So if I take this value and multiply it by minus 1, it goes up to the top and it matches the left side. You see? Yeah, so it's just a mathematical way to say, look at the left and right and see if they're mirror images of each other, or if the, mirror images or opposite in sign. Yeah. Yeah. So that's all. Yeah. Very good. Let me escape out of that one. So we're going to do a tour of Gaussian today, an intro to Gaussian. And so here's you guys. Y'all are in the top 2% now. It says most everybody thinks of Gaussian as a statistical term, but it's also a function. It's also a software package. And so we're going to learn about Gaussian computational chemistry software packages today. But I could go through like the normal like theory behind all of these different pieces, like right here, the level of theory and so on. But there are videos on that, and I would really like to just jump to showing you what the software package can do. Okay, so you can watch the video I'll put up on the playlist that goes through what all these little alphabet soup levels of theory and so on mean. But let me just, I'll cut to this final picture here. First of all, let me just do this right here. This is our particle in a box wave function. Like our particle in a box Hamiltonian, right? The total Hamiltonian is the total energy operator. And when we operate on the wave function and integrate over all space, we solve the Schrodinger equation, we get the energies, right? And we did this for a particle in a 1D box using this Hamiltonian. We go to a hydrogen atom, or any multi-electron atom actually, we get this. Okay. But it's not that impossible, okay? So let's just look at the parts real quickly. This is this upside down delta, okay? Delta equals a change, right? You know that for whatever reason, the mathematicians wanted to flip it upside down to show the derivative, okay? So the upside down delta is the derivative over all space with respect to x, y, and z, okay? Or if we're in a spherical polar coordinates, it would be distance from the nucleus r, theta and phi. Theta and phi are kind of like longitude and latitude on the globe, how far around you go and how far down from the pole you are. So that's the spherical polar coordinates. But the bottom line is every particle in the universe has 3 numbers that tell you where it is. X, Y, and Z, or r, theta, and phi from the center of something, okay? So you can take the second derivative of that, and that gives you the kinetic energy. You got mass in here, you got Planck's constant, so on. So this is exactly like what we did, okay? But it's in 3 dimensions. And this is for the nuclei, okay? And we also have electrons. So we need the kinetic energy of the electrons. Now we have the mass of the electron. We've got, again, the second derivative of the wave functions for the electrons. So those are the 2 kinetic energy pieces. That's Tn, kinetic energy for nucleus, Te, kinetic energy for the electron. Easily done numerically with sums in the spreadsheet. We won't do it in a spreadsheet, but Gaussian will do it, behind the scenes using Fortran programming language. It was written in the 70s with Fortran. Okay. Then we have the potential energy. For our particle in a box, the potential energy in the box was 0. So that made it very nice. Our V was equal to 0, so we only had the kinetic energy piece. But we're dealing with charged particles in a molecule. So we have the repulsive energy of the 2 nuclei, the charge on nucleus A, alpha, and the charge on nucleus beta, and divided by the distance between those 2. So this is the number of protons in each nucleus. This is the electric charge for each of them. So E times E is E squared, okay? And then we just loop through the table. We have nucleus 1, distance to nucleus 2, the charge on both of those, calculate the repulsion. Then go to nucleus 3, 4, 5, 6, 7. We get to the end and we go to nucleus 2 and its repulsion to 3, 4, 5, 6, 7. Nucleus 3 repelled by 4, 5, 6, 7, all the way down. So we can do that very quickly in these nested loops in Fortran. Repulsion of the nuclei. Coulombic repulsion. Then we have the attraction. See a minus sign? It lowers the energy. Attraction of the nucleus and the electron. So this is the distance between the nucleus and the electron. We pick nucleus 1, all the electrons in the molecule. Nucleus 2, all the electrons in the molecule. Nucleus 3, so we sum all of those through. And then we have this piece, the electron correlation piece. So this is the distance between two electrons. Here we run into a problem. Because how are we describing the electrons? What did I fuss at you about your electron, right? It's not a single particle moving around in space. It's the wave. We can square that wave and get a distribution of the electron, but a distribution is not a location. So we only know the electron position by probability. We don't know its location. And it would take much too many computational resources to like infinitesimally pick a location and its probability and then do these sums and so on. And so there's no analytical solution. We do have a lot of numerical approximations, but this is the reason why one, we can't do it by hand. There's no analytical solution for this term because we can't calculate Rij. Now we could pick a location for an electron. Let's say its most probable position, right? And then we could sort of look at the distributions of all the other electrons, their wave function squared, and we could say, well, this wave function for this other electron is kind of between me and the nucleus, and so I'm going to reduce the nuclear charge in order to take into account the shielding of the nuclear charge by the other electrons. And so that's a way to do it. There's lots of different ways to approximate the electron correlation, and that's why we have so many options in our Gaussian software. So when we go in to build a calculation, the levels of theory that we have to pick are based upon this electron correlation term and how we are approximating it. Okay. So let me jump to like I said, don't freak out. We're skipping all this. Okay. I want to get to the one that is, there it is, right here. Okay. So let's think about a cyclopropane, for instance. So everybody draw cyclopropane. Oh, that's a terrible one. Okay. So there's cyclopropane. Everybody okay with that? How many electron domains are around each carbon? We've got one here, one here, one there, and one there. 4 electron domains. So what's the hybridization? We have 4 electron domains. So how many atomic orbitals do we need? We need 4 to make our hybrids. So it's an s orbital and p3, sp3. Okay. What are the angles for sp3 between these electron domains? sp3? That's right, 109.5 degrees is the angle between those domains, and that's that's what we see with like methane, right? So this angle here is 109.5 because that carbon is sp3. Okay. This carbon wants to be sp3 too, but what is this angle right here? 60 degrees. Okay, so how do we get the electrons to bond at 60-degree angles to lower the energy of this molecule if we're using p orbitals? And what are the angle between the p orbitals? 90 degrees. Well, we made these hybrids. Maybe we make some local bonded hybrids, and they're, they can get it 109.5 degrees. But how do we get it to go to 60? That's 90 doesn't work. 109.5 doesn't work. What can we do? Well, we can add d orbitals to the carbon. And we can even though the d orbitals are much higher in energy, look, carbon doesn't have any d orbitals in its ground state. So we let carbon be a little excited in a cyclopropane molecule by giving it d orbitals. And with the numerical methods in Gaussian, we can let it use 10% of a d orbital. We can mix in 5% of an f orbital if we want. Okay, so the more freedom we give the electrons in the molecule, the more like nature it is. Because an electron in a molecule is not going, gee, I really want to bond with that other carbon at 60 degrees, but I don't have any d orbitals. It doesn't know what a d orbital is. It doesn't know what an f orbital is. The d and f orbitals are hydrogenic orbitals. They're the analytical solutions for a hydrogen atom. They have really nothing to do with a molecule. So in order to make the molecular orbitals, we mix the atomic orbitals, and by mixing them, we get 5% of this and 10% of that and 80% of this, and then the electron has more freedom. So that's what we mean by complete basis set. If we give the electron complete freedom, then we match nature. Okay? If we get to complete electron correlation, however we do that, then we match nature. We can match the repulsion term in the electron cloud. We can't do both. We can't extrapolate the complete basis set and do complete electron correlation because we'll be coming down this diagonal and our calculation time goes to infinity. So we don't have the computational resources to do both. So we'll do a really high-level theory with a small basis set, very little freedom for the electrons, and kind of see what a correction term would be. And then we go crazy and give it a huge basis set, but at a low level of theory, and then we kind of extrapolate to what would be in the middle over here. So those are the advanced techniques, but it's just, there's always this balancing act between high levels of theory and large basis sets. If you type in the wrong thing and go crazy on both of those, you'll never finish your calculation. It just won't. So we're not going to really do any studies on that. That's like a whole nother course on trying to do really highly accurate Gaussian calculations. We're just going to do some simple Gaussian calculations and look at the vibrational spectra that we can get out of it. So we're going to learn about spectral predictions, spectral simulations using Gaussian. So let's do some of those. Rather than talk, let's go ahead and just learn by doing. So here's the Gaussian website, or not website, but software. And you have this molecule building window. Let's build a simple little molecule. And also, if you'll notice on Blackboard in this week's folder, down at the bottom, did you notice the new item I added yesterday? Project 2, yes. Now, I did move the deadline. On the schedule, the deadline was going to be next Wednesday. I moved it to the following Wednesday. So you have 2 weeks to do it. Okay, it's not a very big project. It's nothing like the last one. It's much easier, okay? No written work, just a PowerPoint, okay? But your PowerPoint needs to be good. It needs to look nice, okay? So we're going to make a molecule. So let's make nitromethane. I want a molecule, and everybody will have a different molecule. I want you to have a molecule that has threefold symmetry, like a methyl group, and twofold symmetry, like a nitro group. So let's come up here to the R. So we have this one is the periodic table, this first button, in terms of this little builder window. We pick all these different elements. You see the different types of carbon that you can put in there. We have a rings window, and so if we click on here, we have all these different types of rings. Okay, and you can pick here's like chair cyclohexane, and hit undo. Okay, You can pick, you know, this is kind of a fun one. Look at that. It's crazy. Undo. Okay. Let's put an R group on there. So we have all these different R groups. I'm looking for a nitro. Here's a nitro. Okay. So just click there and we got it. We got nitromethane. Yay. Okay. So I like this because it has twofold symmetry. So the vibrational modes of this NO2 will be kind of like water, asymmetric stretch, symmetric stretch, and a bend. Okay. The methyl group will have threefold symmetry. You'll have some things that we'll talk about. We're going to talk about local symmetry later on, and I just want you to have a molecule that kind of displays some of that. So let's do a quick calculation. So we come up to calculate, first item, set up Gaussian calculation. We have job type. So if we did the energy calculation, it would just calculate the energy of that molecule, the electron cloud of the geometry that we built. But that may not be useful because we don't have, we want an optimized geometry. We want to optimize the structure of the molecule, and then we want to calculate the frequencies. So here's this opt plus freq. So we're going to do an optimization of the molecule's geometry and calculate the vibrational frequencies of the molecule. And then we want to compute Raman. It says default. I don't know what default is. I know what yes is. So I want to calculate yes for Raman. Okay. And then so that's our job type. Opt freq, yes for Raman. Okay. Then we go to method. Here's where we pick our ground versus excited state. We're going to just do ground state for all of these. And then the different levels of theory are here. We're going to do this density functional theory and this B3LYP. So that's just been a very nice sort of standard method that's been going on for more than 20 years. And so we'll just use that one. And then the basis set. So we're going to go with 6-31G with the D orbitals on the carbons and the nitrogens and the oxygens. So when we have two options here, the first one is for all the elements except for hydrogen, right? Think about all the organic molecules. They're just bristling with hydrogens. We could save a lot of extra cost if we don't put d orbitals on all the hydrogens because they don't really need it. It's the heavier atoms that need this flexibility in how they bond. Although you might put p orbitals on a hydrogen if you're doing hydrogen bonding. That allows a directional electron cloud on a hydrogen. So maybe if you have hydrogen bonding in your molecule, you'd want to put p orbitals on the hydrogens, and so you come over here and select p. There's no need to do that here. We're just going to leave it at blank. Okay. Then you have a title. You can put whatever you want here. My title. Okay. You put your name in there, maybe your login ID, and your password for your Netflix account, and so that I can use it. Whatever, you know. And so then you have this link 0. We really don't have to do anything with link 0 because now they've improved the software and it puts this parent name into the checkpoint namespace, and so we don't have to mess with that. And then this general. I come over here and I don't like this connectivity thing or the Cartesians thing or the PDB, so I uncheck all those, although it doesn't really hurt you if you leave them checked. And so now we're ready to go. Now there is solvation. I've never really seen any benefit to try and do solvation calculations, and they crash a lot. So not to throw shade on Gaussian, but I've not found that to be super useful. But you might. So if you're doing something in your research, maybe you want to try the solvation stuff. So that's it. That's all you got to do for setting up a calculation. Now you do need to pay attention to this method tab, charge and multiplicity. So if you're doing something that's an anion, or obviously it's -1, whatever the charge is, but you got to pay attention to how many, if the electrons are paired or not. So let's say we made this molecule a -1. Okay, notice the spin. If it's a single unpaired electron, the multiplicity is the number of unpaired electrons plus 1. So it'd be a doublet. Okay, what if we were back at 0? You know, it's a singlet. I have 0 unpaired electrons plus 1 is a singlet. Okay. What about if I was in oxygen? In oxygen, it has 2 unpaired electrons on it. And it's kind of like a diradical. That's what makes oxygen so reactive. And so it would have 2 unpaired electrons plus 1. That's a triplet. Okay, so ground state oxygen is a triplet. Okay. So we're going to go here, singlet, everything's paired up. We're going to hit submit. It says you must save the Gaussian input file before you submit. So where does it save them? It should be in this C G16W scratch folder. Okay, that's the little scratch pad. We're going to do nitromethane. I'd put like a dash, opt freak, and then for class. Okay, so that's me. And then I do .gjf, Gaussian job file, GJF. That's one of the options. .com is the old, like 3-letter extension that for Gaussian files, but .com is also very, like it's used in Windows, and so I would not do that because if you double click on it, it may try to start something in Windows and not try to start GaussView. But if you associate GaussView with GJF files and you double click on it, then it'll bring up GaussView and it will do that. Now this may mean nothing to you if you don't have the little 3-letter extensions enabled to view on your computer. But if you do, then you'll see that it's a .gjf file, which tells you it's a Gaussian job file. And now it's ready to submit the job to the actual software package called Gaussian 16 for Windows. What we've been using is GaussView, and now it's going to start Gaussian. Okay, where is Gaussian? Here it comes. So I'll give you a live narration of what's happening. Reading in all the binary packages, there's the geometry you gave it. And so it's saying, let's optimize this geometry with Cartesian coordinates. It's looking at the number of basis sets there are, setting up the integrations and differentiations. And what it's going to do is it's going to solve for the energy of the molecule. And then it's going to take the slope of that energy with respect to the atom positions and determine whether it needs to move the geometry or not. Okay. Okay, it's done with the first energy. It says SCF done, it gives an energy. Then it looks to see if the positions of the atoms are in a minimum. And if they are, it's done, but it's almost never done the first time. So then it moves the atoms and redoes the whole thing. So it's an iterative process, which means you should never print one of these files because it's 90% junk, right? It's step 1, step 2, step 3, step 4, step 5, and maybe step 10 is the one you want. And why print steps 1 through 9? So you just never print a Gaussian output file, okay? Another SCF done. So SCF means self-consistent field. So it's looking at the electron wave functions and the positions of the nuclei, and it's changing the coefficients on the number of p orbitals, d orbitals, and everything that it's using until it gets a self-consistent field around the molecule, and then it calculates the energy. There's a third or fourth step. If these are going really long, you can go into that file folder and you can copy that file. Use quickly Control-C, Control-V, and so you copy the output file. And then you can look inside the copy. I never open the output file because I don't want Gaussian to try to write to it while I'm in it because it may screw up and kill the calculation, okay? Eventually it'll come up with the optimized geometry and it will start the second calculation, which is the frequency calculation. Now here it does the second derivative of the energy with respect to the coordinates of the nuclei to get the parabola curvature and applies a harmonic oscillator model to it to calculate the vibrational frequencies. So we will get the harmonic frequencies, the harmonic oscillator frequencies for all of the motions in the molecule, the symmetric stretch, the asymmetric stretch, and everything. I should have picked a smaller basis set, so it would be finished already. It has rotational constant. Oh, I saw what I recognized. Now we're in the frequency calculation. It recalculates the energy, then it looks at all of the vibrations, and we'll see the output here pretty soon. Hello. I have no idea what half this means. No, I have no idea what 90% of this means. So if you're looking at it going, this is a bunch of crazy stuff, it's just mostly for debugging, like if you have errors in the software and craps out. But there may be 20 lines out of 1,000 that are useful. Yeah. So that's why we don't print it. Why did I choose B3O? 6-31G. If I'd have done STO3G, it would have been done already. Yeah, so the fewer number of basis functions you use, the faster it goes. So that's something you can take to the bank. You can write that down. Smaller basis set, faster calculation, but less accuracy. Yeah. And the Raman makes it take a little longer. So that's why it's probably taking a little bit. It's a great video. There we go. It does dipole moments and quadrupole moments and all kinds of things. Octapole, hexadecapole. It's calculating the polarizabilities. So polarizabilities are needed for the Raman intensity. There we are. And you always get a quote at the end. And it's always kind of fun to see the different quotes. That has been very helpful to me because if I wanted to say, is this, I'll have duplicates on my computer. In terms of file name, I was like, is this the same calculation? If the quote's different, you know, it's totally different. That keeps you from having to compare everything. Okay, do I want to open up the file? Also, look here. It says CPU job time, 2 minutes, 15 seconds. Man, it sure seemed like a lot longer. And then this says normal termination of Gaussian, and it gives the date. I'm telling you, that normal termination of Gaussian is one of the greatest things you can see when you're sitting on a calculation for 5 days and you keep coming in and shaking the mouse and seeing on the screen and you're like, it's still going, or is it frozen? I don't know, and then you see that normal termination and you're like, yeah. All right, so close that window and open this. Look, we have two options. The checkpoint file, CHK, contains the molecular orbital information. So we could pull that up if we wanted to display the MOs, okay? But we want to do the infrared spectrum, so we're going to open the log file. So we're going to uncheck the CHK and check the log, okay? Let's see what else, what other fun things we can have in here. Okay, this is kind of fun. It says read intermediate geometries. You don't have to do this, but it's fun. Okay, so I'm going to do it right now. Read intermediate geometries. Okay. And we'll hit open. There's our molecule. Okay, so there's our nitromethane. That's the optimized geometry at this level of theory. And what's cool about it is up here I've got, this is panel number 7, so it did 7 steps. So this is panel 1, 2, 3, 4, 5, 6, 7. So that was the optimized geometry. See, it didn't change very much, but it's kind of neat. Here's the energies associated with that. Let's see. Oh no, that's just all the pictures. Where's the energies? Result. Optimization, here it is. Yeah, this is the energies and the root mean squared gradient for those steps. So you can see here's the initial one. You see the little red circle around the energies? So you can kind of see the energies as you go along. So then it changed the bonds and everything, and it dropped the energy and it dropped the slope. And then it overcame some kind of barrier. The next step was much higher, but then the next one was even lower. And then it got to where it wasn't changing anymore, and so it quit. It's never going to be perfectly at the minimum, but it'll be close enough to the minimum that Gaussian says, okay, let's finish. We'll call it good. So it's finished there. Okay, so that's the optimization window. Let's come up here to results and look at vibrations. This is so cool. Okay. So in your project, I have you modify the window to display several things. So you right click on the window, you come down here to view, and you click on Cartesian axes. So there's our Cartesian axes. Now it's put on the center of mass. Most of the time when we draw our molecules, we have it off to the side, okay? But this is on the center of mass. So is it a right-hand rule? Yeah, let's get around here. So there's X coming out of the screen, and Y and Z. So that's our That's our molecule. Okay, so X is coming out, Y is over here, and Z is pointing up. And oh, look at this, we have a negative frequency. That's cool. That tells us we're not actually at a global minimum. So when you have an imaginary frequency, you can come in here and you can animate it to see. Yeah. So the way it's the nitro relative to the methyl is not at a global minimum. So we need to rotate that molecule a little bit and resubmit the job so we could get rid of that negative frequency. Okay. Think of a Pringles chip. You know what a Pringles chip is? You know, when you're right in the middle of that saddle point, all the slopes are zero. Okay. But one of them is at a maximum and the other is at a minimum. Okay. And so where we are on this is we're on a maximum with respect to this motion. And so we would need to go in and change that angle a little bit, resubmit the job, have it go through the optimization again, and we could get to even lower energy. Okay, so I'm so glad that this worked out, because when we talk about negative frequencies, this is called imaginary frequencies, but they're negative frequencies. But isn't that cool with so you can look over here and see the infrared. The strongest peak is, look, 246. So that's the strongest peak in the molecule. Let's do a right click here, view, and let's turn on, oh no, it's over here. Turn on the displacement vectors and the dipole derivative vector. Okay. Let's make displacement vectors a little bigger. So you can see that arrow diagram. So think about water. Remember that the asymmetric stretch on water was the arrows were pointing on the hydrogens moving this way and the oxygen was moving that way. Same kind of thing. This looks a lot like water on this end of the molecule. That's the asymmetric stretch. So the arrow diagram, you see these little blue arrows, this blue arrow, and that long blue arrow? That's showing the asymmetric stretch of this group. And it's kind of coupled with the rocking motion of the methyl group. So the arrows that we draw are supposed to be giving you the same information as the animation. But the animation is clear, right? But we can't draw animation on paper, right? So we use the arrows. But the arrows are supposed to convey this same information. So this project is for you to do the Gaussian calculation and then come here and analyze the vibrational motions of your molecule and then put those screenshots and so on into your PowerPoint and talk about them. Okay? So this is what we want to do. We want to analyze the vibrations. We also want to show that the dipole derivative vector, this orange one here, that's the direction of the dipole moment change. It's the derivative of the dipole moment of this molecule. So this molecule has a dipole moment that goes up and down because this is a negative end of the molecule, the other is a positive end. And so there is a dipole in this molecule, but the infrared intensity is related to the dipole derivative. How does the dipole change with the vibration? So with this vibration, this orange is the dipole derivative. The larger that dipole derivative, the larger the intensity of that infrared mode. Let's pick one that's not so strong. Let's pick this one. And so its dipole derivative is coming along the z-axis, and it looks a little smaller. Okay, let's animate this motion. Yeah, so the nitros really aren't moving, it's just the deformation of that methyl group. Let's pick one with an even smaller dipole derivative. Here's one at 0.5. Well, it doesn't look like it's changing. That should be really small, so maybe they're not. Maybe they're just showing the direction of the dipole derivative, because if it were 0.5 versus 240 something, it would be a much bigger difference. So I'm thinking just from that little quick experiment that this orange arrow is just showing you the direction of the dipole moment derivative. So you can change its size here like this, just if you need to display it. But okay. So that's the animation of the different modes. You could also pick the strongest Raman mode. So this is the strongest infrared mode, the asymmetric stretch. But notice it's not very strong in Raman. This is the strongest Raman mode. Okay. So it's changing those hydrogen positions, so all stretching out. Here's another strong Raman mode, and another one. Okay. Now here's a fun thing. We're going to do some of this in Excel, but not on this project. If we click Spectra here, we get the simulated spectrum. Isn't that gorgeous? Now this is kind of cool. Let me try to adjust my screen. And so for your project, maybe you want to do something similar to this. You might want to have the windows all on the same little screen. So I'm going to make this pretty big, like that. I'm going to scoot this over here so I can see what mode I'm in. Right? And I've got all the vibrations there, and then I've got my molecule. Let me scoot this over like that. Isn't that cool? So I've got my frequencies, I got my infrared intensities, I got the Raman activity, I got the molecule over here, and I've got the spectrum. And I can come over here to the spectrum and I can right click it and do properties. I want to flip the range on my x-axis, invert axis, so that it's very similar to what we see. Yeah, save current changes. Flip the axis on the Raman, so that the high frequencies on the left, the low frequencies on the right. I've got the wave numbers and so on, and so I can hit OK. And see, this is just not a very strong peak in the infrared, but this one's the strongest peak. And you see the little red dot there? That little red dot shows us which mode we're talking about. So I have the animation, I've got the frequency, 1679, I've got the intensity in the infrared, 246, I've got the little triangle, the little red triangle there, and the strongest peak in the spectrum. Isn't that nice? So this is all Gaussian, it can do all of this for us. And so then you can take a screenshot of this and put that in your PowerPoint, and then you can talk about it. Okay. So that's what you'll be turning in. Notice it's a strong peak in the infrared and a very weak peak in the Raman, because the infrared deals with the change in dipole moment. The Raman deals with the change in polarizability. You can kind of think of change in polarizability as the size of the electron cloud. And this doesn't change the size of the electron cloud much, because when the nitrogen and oxygen get far away over here, they get closer over here. So the cloud's moving, but it's not changing size. Yes, well, if I had a question. And then if you go to this big one here, where the Raman is huge and the infrared is small, pushing those hydrogens far out away from the molecule changes the size of that electron cloud substantially. And so that's why this is a strong peak. It's the strongest peak in the Raman, and then one of the weakest peaks in the infrared. Okay. There's already a dipole in that direction on the molecule, and moving those hydrogens out doesn't change that dipole very much. It does change it, but not very much. So it's not a strong infrared peak. Are y'all learning some spectroscopy? And all we've done is, like, just in 1 hour, we've played around with Gaussian, calculated the frequency and Raman, intensities, IR intensities, and we're able to show the spectrum. Let's play around with line shapes. So, properties, IR peak, half width at half height, 4 wave numbers. Let's make it 8. Yes.
Quick question. So when we're talking about
20.
movements, we're talking about rotational, vibrational, and translational, correct? And so what we're seeing with those hydrogens is translational movement, correct? Is that right?
No, because the whole molecule moving is translation. That's why there's always and only 3 translations, because it can move in X, Y, and Z as a whole molecule. Yeah, and rotation is the whole molecule rotating. So even that one where we had the NO2 on one end and the methyl group trying to rotate, that's not a rotation. It's still a vibration. Yeah, it's called internal rotation, but it's not a rotation of the molecule. So we only have 3 rotations possible. For a linear molecule, we only have 2. So there's a restriction on the number of translations. Again, it's the whole molecule, rotation's the whole molecule, and everything else by difference is vibration. Yeah. So here I made the wave, the spectral resolution 20 wave numbers. And so this might be more accurate as to what you get out of a regular, like, low-cost Raman or something like that, like our little fiber optic Raman. That's what our spectra look like. Yeah. And so, like, look at all the peaks that are right here at 1500. There's like 4 or 5 peaks right there. And in the spectrum, we have 2. Like, we have a peak and a shoulder. And so that's another important thing to know, that, you know, you may have lots of vibrational modes under one peak. So if we're trying to say, well, which peak is that? Well, it's hard to answer that question because we have all of these possibilities. And so then we can go to that section of the spectrum. We hit OK here. So around the 1500 in the Raman. Yeah, so just like 12 and 13 and so on. So this one is one of them right here. That's the deformation of the hydrogen, the methyl. And this is another deformation. So it's 2 different modes, but it's the same thing. It's the methyl bends. It's the angles in those methyl, the hydrogen angles that are changing there. So that's why they're both at the same frequency, and they're both a similar intensity. And so you could put a big little star on that peak and say deformation of the methyl group. Okay. What else do we have? And then the one at 1400. Okay, so this one is a good one. This is what we call coupling. So we have the umbrella. This is called an umbrella mode. You ever have an umbrella in a windstorm and it, like, opens up? That's what's happening to those hydrogens. That's an umbrella mode. All 3 hydrogens are doing this together. So it's a funny name. But it's also coupled with this NO2 stretch, because they have the same frequency, the same force constant, you know, different masses, different force constants, but they all give you the same frequency. So they happen together. Yeah. And here's more of a pure umbrella mode. Notice this one doesn't move very much on this one. So these are just different vibrational motions. And this is what some of the stuff you can get out of Gaussian. So how do I take a screenshot of this? Well, do you know about the snipping tool? So Windows Shift S. So write that down. Windows key, Shift S. And it brings up this snipping tool. There's different options. You can select a rectangle, which if I wanted to just capture the molecule, I could draw a rectangle around the molecule. If I capture the window, I'm just going to get one of these, right? One of these windows. If I want the whole screen, obviously full screen. And so I just snapped a picture of the full screen, and I can come over here to my PowerPoint and I could paste it in, hit Control, I just pick a PowerPoint slide and hit Control V and paste it in. So I got a whole screenshot of everything on my window. When you're doing your presentation, and I'm gonna comment on some of the presentations y'all turned in last time. Notice how I take up the full screen on my presentations. Pretend that you're paying for every square inch of space. Okay, because having a lot like this doesn't make sense to have a presentation where I have all of this empty space over here. Okay, I'm paying for real estate here that I'm not using. Okay, and so I mean it can be, you can overdo it, but a lot of y'all had your pictures were too small and could be made bigger, you know. And for people in the back of the room, you need them to be bigger. Yes.
Use negative spacing with lines.
Yeah, well, they're full of crap as business people. Yeah. Yeah. You know. Now, you know, if I have some empty space here, but still, I'm trying to show, you know, this is what I walked through where the Gaussian calculation was going. We calculated the energy. the gradient, the minimum. It was no, we do it again, and then we get the frequency calculation. We have the negative frequency in ours, so we would go in and change that symmetry a little bit. We would rotate one of those groups so it's not stuck in a symmetric well. There was a plane of symmetry in there. If I break that plane of symmetry, then Gaussian can find the true minimum. And then when we get to frequency calculation with no negative frequencies, then we can say we have the ground state or optimized energy data. Okay. Now, what are some other options for your molecules? I think I'm going to go ahead and just assign small molecules to everybody, or maybe a sign-up list where you get to pick, of this list. Like we could do this with the NO2 group. We could also do an NH2 group. We could do just an OH, like a methanol or something like that. And so we want to do a bunch of asymmetric molecules and then do the frequency calculation and then make a quick PowerPoint and talk about what we see. Is that good? That's our project 2. Okay.